Hello, everybody. Today, we invite Professor Marc Dacier from KAUST, King Abdullah University of Science and Technology in Saudi Arabia. And the talk it will be around the importance of research in network security. And I will start by introducing Professor Marc Dacier. So Professor Marc Dacier is a full professor of computer science, and he's right now acting as the Associate Director of the Resilience Computing and Cybersecurity Research Center, RC3 at King Abdullah University of Science and Technology, KAUST, in Saudi Arabia. So Professor Dacier obtained his PhD from IMPT in 1994. From his work done at LAS, CNRS in Toulouse, south of France. And since then, he has had a balanced career between industry and academia. And after his thesis, he worked for 1 year as a security consultant in Paris for France Telecom and the French Ministry of Interior. So in 1996, he joined IBM Research in Zurich, Switzerland, to create the Global Security Analysis Laboratory, GSL, and in 2002, he became a professor at Eurocom Institute. And in 2008, he joined Symantec to build its European research, to build its European research labs. And later on, he spent 2 years in USA to manage all the collaborative research projects worldwide. In that role, he was in charge of teams in France, Ireland, and the US. So he was also the university relationship manager for Symantec Research Labs worldwide. And in 2014, he became the director of the Cybersecurity Research Group at the QCRI in Qatar in Doha, where he lived for 3 years. And in October 2017, Professor Dacier came back to Eurocom, south of France, Sophia Antipolis, to become the head of the Digital Security Department and the full professor until June 2021, when he joined KAUST. He's internationally recognized expert in cybersecurity. Dr. Dacier has served on more than 120 program committees for all major security and dependability conferences, and as a member of editorial board of several top-tier technical peer-reviewed journals. So thank you again, Professor Dacier, for accepting the invitation. And the talk is yours. So if you have any questions, do not hesitate to put them in the chat, and then later on, Professor Dacier will give you the relevant responses. Yeah, you can kick off, Marc.
Thank you very much.
Thank you.
First of all, let me thank you for the invitation. So I want to thank TII, Technology Innovation Institute, for the invitation to give this talk. The talk will be I hope will be kind of an eye-opener for the people to see the situation we are in with respect to cybersecurity, and more importantly, where we are going. And I think there is an issue with network security that hasn't received the attention that it deserves. So without any further ado, let's go into the presentation itself. So my talk overview, there will be an introduction and conclusion. So in the introduction, I will really look at where are we right now with respect to security. We have been working on it for more than 20 or 30 years. Can we actually really claim victory? I'm afraid not really. And I will list a couple of issues we have. First, we have long-lived old bugs that have survived for a long time. That's bad. But we also have made progress in building security software, but actually those software themselves have security problems, which is probably worse. And then what I will also cover is the economy of scale that actually the bad guys are benefiting from, in the sense that now we start discovering more and more often problems with libraries and open source components that are used in a very large amount of platforms, and that is even worse. And last but not least, we will move into network security. and more specifically network protocols, because there it's an even bigger problem in the sense that we have a large number of network protocols that have been used for many years, and we haven't really paid attention to the fact that the protocols themselves, the semantic of the protocols themselves, are problematic or can be misused to do bad things, and that is really, really bad. So, this looks pretty bleak. So the conclusion, maybe we should admit defeat, that, we are not going to make it. It's not getting better. And just spoiler alert, I think there are things we can do. But yeah, we have to be serious about it. So some historical context first. Remember that the internet is not old, not really old. I mean, January 1st, 1983 was the so-called Flag Day. This is the day where everybody in the world, people have said, okay, we stop everything, we get rid of the network stack we have been using so far, and we install TCP/IP. And this is something that we were able to do at that time worldwide because there were not that many machines connected. So it was possible to synchronize all that. Imagine today, we would love to be able to do that for some of the protocols that we have to live with, but that's impossible. But that was only like 40 years ago, right? So it's nothing. I mean, among those attendees, maybe there are young students and they think, oh, 40 years old is 40 years is very old. But no. For me, it's not old. It's very young. So the protocols we deal with, DNS, and we will talk about it later today, the RFC dates from 1983. So at a time where the internet was not even connected, or the NSFnet as it was known at that time, was not even connected to any commercial network. So there was only a bunch of geeks, professors, universities, researchers, using that network to exchange technical reports and papers and data and stuff like that. But there was no streaming or buying anything. It was completely insecure because SSL was only introduced in 1995, which was supposed to be, oh, hooray, now we have secure transaction. We can have secure transaction. I mean, at that time, we thought SSL2 was secure. We know now it was not, but that was the beginning of basically e-commerce, right? And HTTP actually was created around the time in May 1996. That was the first RFC on the HTTP 1.0 protocol. So that's just to put things in context that initially there was no security at all because there was no bad guys. It was just for universities and so on. And some of the key protocols that we are still using today, even though they have been evolving and so on, dates from that time. And the security problems, or the people looking at security problems, this is also very old. I mean, Aleph 1 wrote his famous paper, Smashing the Stack for Fun and Profit, which is really the key seminal paper on understanding what buffer overflow is and how to take advantage of it. That was in 1996, and he published it in the FRAC magazine. And after that, lots of people have looked at it, and there are lots of different kinds of attacks using the same principles, using format string and heap-based overflow and so on and so forth, have been proposed. But in 2013, we had a pretty good understanding, so much that a paper has been published in IEEE S&P, which was a SOC paper, a systematization of knowledge, really summarizing, providing a global entity to position all these different notions in terms of what are all the problems, what are all the solutions. That was like 10 years ago. So these are very old problems. Nevertheless, you will see today that until today, these very well known, very well understood problems like heap-based overflow are still found to be big vulnerabilities. Like we have last year, there was a vulnerability on the sudo program. I'll talk more about that later today. Also, when it doesn't come to code per se, but to basic cryptography principles, like we all know that in cryptography, what is very important is to have random numbers in order to generate keys and stuff like that. So as early as a couple of weeks ago, in 2022, the Open Money API, which is Open Money is an online bank, they have an API, and that API was found to be vulnerable because they were just using a mathematical function from a JavaScript that was very well known not to provide cryptographically secure random numbers. And because of that, whatever they were doing with it was insecure as well. And if you look at the development page of that function, it is explicitly said, there is a big box in which it said, don't use this for random cryptography number, for cryptography sound random numbers. Anyway, so this is where we are. The internet, you can say, well, it's not secure, and the way it's designed and the protocols we use, they are not secure because they have been designed with 7 design principles that actually have stood the test of time. And they were extremely innovative and revolutionary. And I really encourage you to read that paper, which is indicated there in SIGCOMM in '88. Because it really explained what was the philosophy of designing the internet the way we have designed it, the way they have designed it. Nevertheless, it's really worth noting that the word security is not mentioned a single time in this 10-page document. And that explains also why we are where we are today. We cannot blame them because as Janet Abbott mentioned in a book she wrote on inventing the internet, they thought they were building a classroom and it turned into a bank. As I have said at the beginning, there was no assumption about bad guys at that time, and security just came afterwards. But today we are in this pretty bad situation. There is a link there where they have 34 different alarming statistics. I have just taken a couple of them. We see the security attacks that are increasing, lots of DDoS attacks. Cybercrime is costing us a fortune, even though we keep spending more and more on building a more secure system. And last but not least, we have a big security workforce shortage, almost 400,000 open slots in the US, more than 2.5 million worldwide. And those people who have a job and who work in security, a recent survey by Symantec is showing that 2/3 of them actually are thinking of leaving their job because they think this is a mission to failure and they are completely overburdened and overloaded by lots of things that they have to do. So yeah, it's not really good, right? So nevertheless, oh yeah, and I want to show the number of new vulnerabilities we find every year keeps growing. So last year we had more than 20,000 new vulnerabilities. And this year we already are almost more than 10,000 and we only are in May. So, you know, if things keep going like that, we will break a new record again this year. So, hooray. But it's pretty sad because if you look, the cybersecurity community has done lots of good stuff. There has been very good work, nice research, nice solutions found, new technology provided, and every time you have the presentation of a funded project by any agency in the world, of course, we always say that we have had impact or that we will have impact and so on. But the reality, as you can see, as you have seen from the previous numbers, seems to be slightly different. So we could ask ourselves, have we really failed as a scientific community to not to produce the knowledge, but to actually to transition the knowledge into something, into actionable knowledge and into product and into deployed products. So probably yes, we have failed, but I just want to temper that a bit because we are certainly not the only ones. I think this is a generic problem across all disciplines. And I would just give you an example. If you think of people who have been working on climate change, they've been working on it for decades. They have warned people. They have shown convincing numbers and proofs and so on. And they have also found solution. But I think the situation is best represented by this sculpture by the artist Isaac Cordal. I'm not so sure they have done a really good job. Not their fault. I'm not blaming them, but that's the reality of the situation. So So it's important to look at it, at the situation in the cybersecurity in a honest way, but we should not stop doing anything and saying, oh, we are bad, we are bad. It's a generic problem and we have to address it openly. So we also have to admit and acknowledge that we have a lot of very good technology which has been proposed. Here I list a couple of acronyms that refer to some of these technologies. We love acronyms, like any community. And I have only put there the acronyms that correspond to real technologies or solutions. I have avoided all the acronyms for all the crypto algorithm or all the acronyms for all the regulations and all the legislation that have passed, because then I would have had like 5 slides just full of acronyms. But there are lots of things. So honestly, we can say that, the situation is much better than it used to be. And every year it is better. And we have more people doing really good job. Our computers get more secure. We do not see these big worms spreading all around the world in a couple of hours, as we used to do in the early 2000s with Code Red and Nimda and these kinds of worms. So much that people sometimes feel, oh, no, there is no problem. I have my antivirus, I have a firewall, and there is somebody else who takes care of security. I don't really need to do anything. No, we have to be very careful with respect to complacency and negligence. And it is not, there is probably somebody else who is in charge of it, but it's also your job, because there are lots of attacks that actually start by the human being. So every human has to act as a human firewall itself, not to click on anything and not to provide information here and there and not to do anything stupid. So we have to keep that in mind. Remember in the early 2001, Oracle came with a big PR campaign saying Oracle is unbreakable. People were kind of surprised, and then they looked into Oracle, and then there were people who started saying, oh, you think you are unbreakable? Okay, we'll show you you're not. And every week there was a new vulnerability published that was actually breaking Oracle. So that was extremely bad publicity. And because when people start really looking at stuff, something that you thought was pretty secure might prove not to be very secure. And it is true for our own systems. People think, oh, Windows is bad from a security point of view, but Linux is pretty good. So, well, yes, there are numbers that show, yeah, Windows had all these issues and so on. But now that we have more and more platforms running on Linux in industry and on web servers and so on and so forth, people take a closer look at Linux as well, the same way people had looked closer at Oracle. And we see that, oh, there were old problems that have been there for a long time, and they are very serious. So I'm just going to give you a couple of examples here. For instance, a very famous case was the Dirty Co attack, or vulnerability more exactly. It was in 2016. It's a Linux kernel vulnerability. Which is amusing is that it can actually be exploited remotely. It does not leave any trace in your system if you're attacked. And it's something that actually got fixed 11 years before, because it's an 11-year-old bug by Linus Torvalds. But then he removed the patch because it was causing some issue with a mainframe, an S390, IBM S390 mainframe at that time. What is also very interesting about Dirty Co is that this is actually a race condition problem. It's what is called TOC2, time of check, time of use. And race conditions are not new. They have been known for a long time, even since the very beginning that we started using time-sharing system. So the Turing Award lecture in 1990 by Corbado actually is it's a very interesting paper called On Building Systems That Will Fail. I highly recommend reading it if you haven't. It's a very good paper. Even now, it's still very important to read it. And actually in it, it describes a race condition that he had to be looking at in the early 60s on a CTSS system, so time-sharing system. And So this is not new, and we still face these problems in at the really deep of our system, in the core of our system, in the kernel. Then you could say, okay, yeah, but that was a long time ago, so yeah, we overlooked that, but no, we are not going to do this problem. Okay, fine. Well, this year there was dirty pipe, which was discovered by Max Kellerman, and dirty pipe is basically the same problem as dirty co, but for other kernel at another place. And again, it enables you to run commands as root. That's pretty bad. Another example, yeah, there is a SCSI system, which has been introduced in the kernel 15 years ago. And people in 2021 have discovered 3 distinct vulnerabilities. And the bad thing with those vulnerabilities is that you can then be root on your machine if you exercise them. And you can do that even if your kernel has been configured with the state-of-the-art security mechanisms that are listed there. So, okay, that's bad, but you can say, yeah, this is because this is the kernel. The people were looking at the kernel do not really look so much into security, maybe, and it was a long time ago. And since then, you know, we have enriched our system with security measures and software that definitely improve the situation. Well, actually, it's true, but the problem is that what we see is that we have built software, secure software, to improve the security, and then you realize that some of these secure software themselves have vulnerabilities. So I've mentioned the sudo vulnerability in the past. It's been discovered last year that it was a 9-year-old bug, even though sudo is a program that is supposed to improve security by helping, by removing the root privilege to user and only granting them at certain moment for certain actions. So it's a very good program, and everybody should be using it. But this case, there was a heap-based overflow. Remember what I said at the very beginning? 2013, there was a systematization of knowledge paper about it. And this heap base is made possible because they have failed to escape properly backslashes in the argument, which is basic sanitization of the input. And then you wonder, how is this possible? These are people who, there is no the excuse of, oh, these are kernel people looking at performance and deep thing. No, this is security people. If you write sudo, you are a security person and you should better know. And well, no, it's still there. The reality is it is there. You want another example? I can give you the eBPF vulnerability, also discovered last year, also in the kernel. Linux extended Berkeley packet filter is also a security mechanism, which is there to enable the people to run programs in a sandbox. So it's really nice. It's very powerful. It's a great piece of software. But again, there is a local attack that enabled people to misuse that system to actually have root privilege on the machine. And to make things worse, somebody thought it was a good idea to publish a proof of concept and make it available on GitHub. So that's bad. And that was last year. And that was a security mechanism. And there are lots of others that I could have given you, but I just want to keep it short for the sake of timing. So, okay, you can say, yeah, there are old bugs in the kernel. Okay, but we're going to fix them. And yeah, we have better security mechanisms now. Okay, yes, some of them have problems, but we know that, we find that, and we fix that. Okay, good. Now, there are worse problems. It's the problem of libraries such as glibc. So glibc is actually a library, a core component of Linux, which is used to implement C libraries. And lots of applications of all different kinds do use that libraries in whenever they write the code of their application. And so whenever you have a vulnerability in glibc, like there is one that has been found in 2015, then all the application that use that library and make use of the function which is vulnerable, then suddenly become also vulnerable. But it makes the tracking of all the vulnerable platforms, the identification of the attack surface, if you want, it makes it very, very complicated because nobody knows all the applications that actually use glibc. And those who have developed the application do not necessarily either know that they have used it, or especially if this is somebody else who has written the code years ago, or actually, even if they know, they do not necessarily follow all the mailing list about all the new vulnerabilities, because as I've shown you, last year there were 20,000 new vulnerability published. If you don't have a very sound mechanism in place to follow up all the applications that you have, and using which component, external component you have used, and figuring out, okay, that external component, oh, there is this old stuff, I should fix it in my code, then you can go there. Worse, with glibc, the security problem has actually been found in 2013 and fixed, but without saying to the community that it was a security problem. So some people have not applied the patch because they had forked branches, and so they never thought that, oh yeah, I should actually do the patches that they have done in the other branch, because it's a security problem. It's not a new functionality, it's a security problem, and I am vulnerable. So, and again, it was a heap-based buffer overflow. Another example is Ripple 20, which was discovered in 2020. That one was like the epiphany for lots of people and a real eye-opener, because the GSOF Research Lab found 19 vulnerabilities in a low-level TCP/IP software library. Everybody uses TCP/IP. So and that library was developed by Trek Inc., a company, and it was actually used extremely widely. There are an estimation of hundreds of millions of devices that actually have that library running their TCP/IP stack. And they have used this vulnerability Ripple because for them it captured the supply chain ripple effect. And I'm quoting the report, it says, a single vulnerable component, so it may be relatively small in and of itself because it's a small TCP/IP library, can ripple outward to impact a wide range of industries, application, companies, and people. Because among those 19 vulnerabilities, some of them were remotely exploitable, and they could give you access and run any command you wanted on machines. It could be done through DNS queries or replies. Some were just built by crafting packets in weird ways, using fragmentation or tunneling and stuff like that. So the two reports I'm giving there provide all the details of that. It's a fascinating reading because it's just TCP/IP. You would think we know how to implement TCP/IP, but 2 years ago, 19 vulnerabilities have been found. And even though all these problems can be fixed, you can be sure that there still are millions and millions of devices out there who are vulnerable to those because nobody actually fixed the firmware or the embedded system code that actually is based on this library. So that is really, really bad. And so much that people saw, oh, this is actually cool. We should look into other similar libraries. And guess what? No surprise. This year, the Nozomi Network researchers found that in another library called UClibc, which is actually also used by major vendors such as Linksys, Netgear, Axis, embedded Gem2, which is specifically used in many IoT devices, and a fork of it, which is UClibc NG, which is used in many operating systems for routers. Same thing, they had a bug there, and that bug is simply DNS transaction ID, which is predictable. So remember what I said before about predictability of number? Well, in this case, the DNS transaction ID is a number. If you can guess it, then you can actually respond to a query without being the real server and without even having seen the request. And so you can do DNS poisoning, and if you can do DNS poisoning, then you can do man-in-the-middle attacks. So it's very serious. It's really bad. Worst is that the bug remains unpatched because the developer of that open source library said, I don't know how to do that. So here is actually just an excerpt of an exchange of email between the Nozomi researcher and the maintainer of that code. They offer to give him some GPG key to exchange securely. And he says, no, you can publish here in this public open mailing list. This is taken from a public website. And it says, share all the details here. I wasn't able to fix the issue, but members of our community will do it for me probably. So I'm not blaming the guy, because the guy wrote this library years ago, and companies have decided to take it over, and it's their responsibility, right? So it's probably the guy is not even making money out of that. I don't know. I have no idea. So whether he wants to fix his code or not, you could say this is his problem. The fact that it has consequences on companies that have just freely used it, you may not want to make him accountable for that. But it's definitely a big problem. And it's just one component. There are others. As we have recently seen with the Russian invasion of Ukraine, people have started using these open source software. You know that there are lots of open source software components with dependencies and so on. And when you make a fix, then your computer will automatically, regularly update itself to always be up to date and so on, which is good security practice, I would say. And so what some people have done, they have generated what is called protestware, and they have added into these pieces of code, they have introduced a logic that is detecting whether or not the code is executed by a machine which is in Russia or in Belarus. And in that case, well, they do something different and bad, like deleting all your files or showing some message or whatever. And it's not only one, there are actually a spreadsheet maintained by a Russian person that has 25 packages where people have done that. And there might be many more, we do not know. So I'm not questioning here the ethic dimension of that. I'm not saying it's good or bad or whatever. That's not the point. The point is that this phenomenon has highlighted the extreme fragility that we have with respect to the dependencies that our systems have by using lots of components, be them libraries that are well established but buggy and not maintained, or actually open source pieces of software that lots of individuals may decide to interact with for good or bad reasons. So, okay, so we have seen kernel, yeah, it's old. Security software, yeah, but we should fix that and we know exactly where it is. Okay, now we have seen libraries and we have seen open source components that are, we don't know where, a bit everywhere. Huge impact. And now we have even worse, which is network protocols. Because, and I call this an almost uncharted territory, because we haven't seen that many attacks in the wild yet. We have seen some, we will see, but not so many that actually are really taking advantage of the semantic of the protocols themselves. It's not an issue of implementation now. It's an issue of the protocol, the way it's defined, the way it's ill-defined, the way its definition keeps ambiguities or uncertainties, and then people implement it in different ways, correctly from a code point of view, but maybe incorrectly from a semantic point of view. Or maybe the protocol itself is such that it can be misused for bad purposes. And that is a real problem, because as opposed to the other code, where you can say, oh, we fixed the code, you cannot just fix the protocol, because you have to redefine the protocol. And sometimes it's not just one protocol, it's actually several protocols that work together, and each of them you can say it's good, but when you combine them together, there is a problem. And where do you start to fix things, and how do you do that? And even if you do, how long is it going to take? Several years. What do we do during those several years? So let me give you a few examples of that. So first of all, BGP, BGP, Border Gateway Protocol, which is the de facto routing algorithm on the internet. Security of it has been well known, or insecurity of it has been well known. There has been paper for almost 15 years. Pierre-Antoine Verviers, one of my PhD students, has done a pretty extensive work on that. And when we were publishing, people were saying, no, BGP attacks, that will not happen. It's too complicated. You need a BGP peer. You need to collude with an ISP. It's not going to happen. And it was not happening that much, but we were still seeing weird stuff at that time in 2014. Now we have a growing number of big cases. I'm just listing there a couple of them. 2017, traffic from Google, Facebook, Apple, Microsoft, MasterCard, Visa have been, for no good reason, routed through Russia. In 2019, the Australian government discovered that actually the traffic to its Department of Defense was actually going through China, even though that wasn't the normal route to go through. And it lasted for 30 months because nobody's watching. In 2020, there was a nice, quote unquote, BGP hijack that people have carried out in order to steal crypto money from a cryptocurrency. And they managed to steal almost $2 million this way. That was the first really big BGP hijack run by bad guys. And it's not trivial to run a BGP hijack. You need indeed an infrastructure. So that means they have it now. Again, in February 24 this year, the CERT in Ukraine found out that actually there had been a BGP hijack realized by Russia against a Ukrainian bank. So BGP is a ticking bomb in the sense that it is very well known that really bad stuff can happen. For many years, people have said this will not happen because it's like a bit of a nuclear bomb. People are not going to shoot themselves in the foot. It's too visible. You cannot really use it to make money. Well, now we have seen a couple of cases where people have succeeded, and my fear is that we will see more of that in the near future. DNS is the other elephant in the room. So DNS is used absolutely all the time by everything. And DNS poisoning is a big issue. It's been known since Kaminsky work in 2008. In 2018, there was a big DNS hijack leveraging BGP. So they have done a BGP hijack in order to do a DNS attack. And they have done the DNS attack in order to actually steal money from another cryptocurrency, MyEtherWallet. And again, apparently from what we know, they have been pretty successful in doing that. So another way of using BGP hijack to actually attack DNS. So, and even more recently, there has been a major DNS hijacking campaigns that has been pretty successful again. So you could say DNS, problem solved, we have DNSSEC, because DNSSEC is there to make these attacks about poisoning kind of impossible. The problem is that DNSSEC has been defined in 1997. That was the very first RFC, 1997, 25 years ago. And today, even though the top level domains have adopted the DNSSEC for their own domain, when we look at how widely is actually DNSSEC validation used by the end users, we see that it's less than 30% worldwide. So that means attacks are still very widely possible. I just show you the number for Saudi Arabia has 97% validation, Emirates 14%. So it varies widely from one place to another. DNSSEC is the answer, but DNSSEC is the problem also, because now people are using DNSSEC for reflexive denial of service attacks. What is a reflexive denial of service attack? It's you have the following principle. I send a request to a server and I send X byte to the server. And if the answer from the server is Y, which is X multiplied by an amplification factor, and if this communication is taking place using UDP, which is typically the case for DNS and DNSSEC, so I send a request to a DNSSEC server, the DNSSEC server sends back to me the IP corresponding to the name, plus a big certificate. That's pretty big. So in DNSSEC, the amplification factor can be 50 to 170. So what do I do now? I send a request to the server, but I spoof the source IP so that the server will send the response to a victim. And I send many requests, and so he will send many packets, much bigger, so I can actually multiply my available bandwidth for the attack by 50 or 180. And there is another very cool protocol called memcached, which is which has recently received a lot of deployment, in particular with big sites like Facebook, Twitter, and YouTube. I don't want to go into the detail of what it does, but with memcached, there you can have an amplification factor of more than 50,000. So I send 1 byte, the server is going to send 50,000 bytes. So now, since there are tens of thousands of servers like that in the world that I can take, that I can actually query and send packets to, then you can see that even with a limited bandwidth, now I can launch super big denial of services against potential victims. And there will be a very cool paper published next week at DIMVA on that memcached DRDoS attack. So it will be probably soon available on the web. So another protocol that we all work with is HTTP. And there is a problem with HTTP, which is HTTP smuggling. So HTTP smuggling is when you have a client that speaks to a server, and in between there is a middle box. And that is very much more frequent than you think. It's very frequent to have a middle box. It can be a cache server. It can be a traffic loader, a load sharing server. It could be a web application firewall, for instance. The problem is when the implementation of the middle box, the way it parses and understands the syntax of the HTTP header, if it is a little bit different than what the server is doing, these differences can be taken, an attacker can take advantage of them to run specific attacks like cache poisoning, session hijacking, cross-site scripting, and completely bypassing the web application firewall. And these attacks have been known since 2005. There was some seminal work by Watchfire, and really nobody paid attention to that when they talked about it at that time. Probably because in 2005, there were not that many middle box being deployed, but now they are a bit everywhere. And for the last 2-3 years, suddenly lots of people in the Black Hat community have started looking at it. And you have almost since 2019, almost every year at Black Hat US or Black Hat Europe, you have at least 1 or 2 papers explaining, oh yeah, here is another way to do HTTP smuggling. Here's another way to do it. And oh, there is a big case I found to do this, to do that. And that's actually, for instance, HTTP smuggling is a very good technique if you want to actually hack into web servers that are in the cloud, because machines in the cloud typically have a middle box before them. And in particular, if you have environments where you have HTTP 1 and HTTP 2, which are 2 different languages, you might actually speak HTTP 1 to the first middle box, but then middle box speaks HTTP 2 to the end server. And there are ways to actually take advantage of the translation that needs to take place to make sure that some things got lost in translation, basically. So these papers, and also the one by the Web Security Academy, they are very interesting if you want to know more about that. And there will be a paper next month at DSN, also exploring that problem, but in a more scientific, systematic way, and on how to take advantage of the semantic gap. So, and that is, again, it's really problematic, because here it's not just HTTP. It's the fact that HTTP has lots of headers that have been added by different application and server and so on. They're not necessarily part of the definition of the language. And And even if what is part of the language, like differences between HTTP 2 and 1, there are ambiguities. And so it is left to the people to interpret and to fill in the gap. And if they fill in the gap differently, then we have a problem. So it's really, that's a very interesting problem, and it's a very, very hard problem to solve. So much that April, Apple actually paid a bounty to researchers who actually had found that they were vulnerable to some HTTP smuggling. They paid them $36,000 for the finding and for helping them to fix that on their own web servers. So we have another issue in terms of protocol with the so-called zero-conf protocol, and I will be very quick for the sake of time. So the zero-conf protocol, your machine speaks it and you don't know it. It's a machine that you connect to a network. They want to be able to tell who they are, what IPs they have, what services they offer, and they want to be able to find out the others around them. And there are a number of different protocols that belong to that family, like Bonjour, LMNR, and others, MDNS, and so on. This is how, for instance, your computer finds that there is an Apple TV that you can do screencasting, or a Chromecast, or stuff like that. These are the protocols. And as we have shown in a paper published in 2021, these protocols offer a huge attack surface, which is very easy to take advantage of in order to run man-in-the-middle attack. And that's really a ticking bomb, because very few people have looked at that in a very specific way. And my fear is really to see malware who will start taking advantage of that. Another one is WPAD. WPAD is another protocol that your machine speaks that you do not know about. And it's a very useful protocol that aims at automatically configuring the web proxy that your machine needs to use in order to access the internet. And this is something that companies use in their intranet if they want to make sure that the traffic to the outside world is kind of secure and controlled. They want to make sure you're not exfiltrating data, or they make sure that you're not attacking somebody. So you don't go directly to the web server, you go through a WAF, a web application firewall. And how to find where the WAF is actually the job of WPAD. But WPAD is completely broken. Worse, it's not even defined. It was defined in an internet draft in 1999, but that internet draft never reached the stage of an RFC. So even though it's never defined, it does not exist formally, it is supported by most browsers and most operating systems. And it runs by default on Windows 10, and it runs by default on a number of different other platforms. So again, this is a big problem. It's a big, because this is a kind of attack that you can be attacked by if you are in an airport, and then your machine gets compromised. And when you go back home in your home environment, you will still be vulnerable to it. So it's pretty bad. It's really bad, and didn't get the attention and the coverage it needs. I have no time to talk about OT protocols. So OT is operational technologies, things you find in manufacturing plant and so on. But last week, Shadow Server Foundation published the results of the daily scans they do. They look for machines that actually speak those protocols on the internet, and they found more than 60,000 of them. And makes no sense. Those machines should not be connected to the internet. These are protocols that you speak within an oil rig, within a manufacturing company, within, automotive factory and stuff like that. So, and of course, these protocols are completely insecure. So that means that probably among these 65,000, many of them could actually be used as an open backdoor to actually break into, and from there go into the factory they are attached to. So it's a major concern as well. And that's just a few examples, but there are many other protocols like that: ARP, LDAP, and NTLM, SIP, and the list goes on and on and on. Some of them have already been exploited, and people mostly in black hat communities and DEF CON and these other places have shown, oh, I can break this, I can break that. But it's a pity that as a security community, we are not systematically looking at them and trying to really come out with sound approach to actually secure us, because that's a big problem and not something we can just fix with a patch. So what are my conclusions? Well, as you have said, we are living in a not so very virtuous circle where we have old bugs, we have new bugs, we have new guys running attacks differently, we produce new technology, but it also has bugs. People work hard to find solutions and propose those solutions, and nobody cares in the technology world or in the real world, until something big happens. There is a big attack against this or against that, and then people say, oh yeah, I'm going to take your solution here. And we go back and we, of course, all the other solutions that should also have been taken with, they are not taken. We just take, the least expensive one and we just do it. And we go on and on and on. It's not great. And that's unfortunately the way it works. We really need to have a plan B. We really need to start looking at things differently. We need to acknowledge the fact that bad things have happened in the past and they will keep happening. There is no way around. I mean, you have seen all these old bugs. You have seen these new software for security that have bugs. You have seen these libraries that are prevalent everywhere in the world. And worse, now I've told you about these protocols that will not be removed. They are there to stay and they contain lots of issues. So yes, we should do our best to prevent bad things from happening, antivirus, firewall, secure software, blah, blah, blah. Yeah, everything we have classically done, we should keep doing it. But we must also have a fallback plan. We have to know that bad things will happen. And when they happen, we need to be prepared. We need to have a contingency plan. And we need to have a way to fix the problem. What if tomorrow your OAuth protocol, which is the one that everybody is using for single sign-on, when you go on a website and you say, do you want to sign on with Google or Facebook or whatever, that's typically OAuth behind a protocol, which is fairly complicated and very easily to misconfigure. What if OAuth has a fatal flaw tomorrow? Can you immediately switch to another form of authentication for your millions of users? Have you thought about that? You need to have a plan and you need to have a way to remove and repair the system that you are dealing with. And you need to continue assess the security of your system. Am I today more or less secure than yesterday? So this is actually what the people in the dependability community have done for many, many years, initially more with accidental faults. So like a thunderstorm or a flooding or whatever, but also with intentional faults, malicious intentional faults, which are the attacks. And so they have conceptualized all that, and in their jargon, if you want to build a system which is dependable, which basically means deliver the service which is supposed to deliver, you need to use 4 families of techniques. Fault prevention, prevent bad things from happening. Fault tolerance, when something happens, you need to detect it in real time and deal with it in order to recover. And then you have to have fault removal to actually, once you have deal with the big problem, like stop the fire, then you need to also remove the cause of the fire, and that's fault removal. You need to have techniques in place, mechanism, protocols, procedure to actually do that. And last but not least, for forecasting, to actually assess the probability that something could happen at some point in order to decide if yes or no you should invest more or less, and if yes, where. It's not just about security by prevention, it's about resilience in general, making sure that no matter what happens, no matter what change occurs, you are still able to deliver. So I will use some quote from the Corbato Turing Award paper to end this. He said, things usually go wrong, sometimes in dramatic ways, and the question to ask when designing such system is not if something will go wrong, but when it will go wrong. And what is needed is constant vigilance against a long list of what if. And remember, that was written in his Turing Award paper in 1990. Thank you very much.
Thank you so much, Professor Marc. Thank you very much for this clear presentation and for this talk. So for the audience, do not hesitate to, put your questions in the chat. I have one question, Marc, on my side. From an IoT perspective here, how efficient right now, those intrusion prevention or detection systems, how efficient they are to figure out, and detect the security issues and characterize them, and at different levels of abstraction, and perception level, at network level, but also at the physical and application level.
You mean did you say from the beginning, from the IoT point of view?
Yeah, perspective. Here dealing more with LP1s, low power wide area network, like LoRa protocol, Sigfox, and so on.
So actually the IoT devices, well, first of all, we have, I have a specific presentation on specifically IoT because it's a very overloaded term. It's not clear what that term means for everybody, but let's say gadgets, right? So all these little things, so IP-based or not. So these devices, what they have in common is that because they are low gadgets and people want to deploy them easily, most of them heavily rely on these zero configuration protocols that I have said. So the zero configuration protocol have existed for a long time, but very few people were actually using them. And now all these gadgets, if you buy these gadgets, you will see that actually they speak those protocols heavily. And that's how you can actually find that, oh, I have a thermometer which is available. I have a hygrometer. I have a CCTV. I have this, I have that, because they announced themselves. You didn't have to configure anything. And the zero configuration protocols are a big issue. Second problem is that most of these IoT, the problem is that they comes with an application on your phone, right? So if you deploy, let's say, a thermometer in your house, you want to be from your office, you want to check what's the temperature at home. But that thermometer is behind a firewall. So normally your phone cannot directly talk to the thermometer. So how does that work? Well, there are different solutions. Some are less secure or more insecure than others. So for instance, some of them, they will take advantage of a protocol which is called UPnP. And they basically will talk to the firewall and say, hey, I am behind you, but I need to be contacted by people. So if somebody comes and knocks on the door on that port, please forward that to me, which is completely stupid, completely insecure. But this is the way some of these systems work. Others will actually call home. They will actually contact a server on the internet, initiate a connection, which is okay because this is from inside to the outside. And they will say, I am there. And if somebody needs to contact me, then use this ongoing connection to send me the request. And your phone will actually connect to that server, and the server will basically forward the request or will serve you the data which is in the server, right? So you could say, okay, that's fine. No, it's not fine, because who knows how secure that server is? You don't know. If that server has been badly implemented, and there are many reasons why it could be like that, if I can break into that server, then the next time your thermometer is contacting me, if in the protocol that they use, there are some issue that like a buffer overflow or something like that, then I could use that link to actually break into your machine, and now I am within your house. So, there are lots of issues with those, because those little things, those gadgets, they don't cost a lot. So typically they have not been designed with big teams with lots of security expertise. And many of them suffer from many vulnerabilities in the code of the application itself. And worse, many of them do use the libraries that I have mentioned before. So it's a huge target, and it's a huge attack surface that is dormant there and people are not aware of.
Okay, so I've got a question from the audience. So the question is, what are your thoughts on leveraging recent hardware security extensions like Intel CET for making program analysis-based approach scalable? So the suspicion of, the author of this question is that there are an interesting approach to detect vulnerabilities, but they do not scale or one compromises precision, leading to false positive negatives for scalability. And we need to revisit those techniques in the light of newer advancement in hardware, for example. So go ahead.
If I put my scientific hat, then I say, great, yeah, let's invest into hardware security and have some define, because basically what it comes down to is to have what is called a TCB, right? A trusted computing base, a place where you can make sound assumptions for good reasons about the confidentiality of the data which is there and the signatures you can achieve and so on and so forth, and the verifications and so on and so forth. So you have a little, as small as possible, but completely secure, ideally provably secure. So that's great. The paradigm seems good. Now, if I put my real world hat, I have to acknowledge that almost all the machines in the world have had the PC, the laptop, the desktop, they have had a TPM component for many years. They are there, and they could be used for something as basic as network access control to prove that your machine connects. If you do secure boot with your TPM, you could prove that your machine is not infected, does only contain the software that it's supposed to have and no malware which has been installed by somebody or any insecure software. And only then will you be allowed to communicate on the network on the intranet of a company. So that exists, it's there, is well documented. The reality is that it's barely used. I mean, it's used in some environment, but extremely rarely. And I would say that 80% of the people who have a desktop or laptop don't even know that they have a TPM. They never use it. Why? Because that requires, from a management point of view, it is very complicated. It is imposing a lot of constraints. Now you cannot install whatever you want. Now you have to know exactly how the machine should look in order to let it go in, and so on and so forth. So from a usability point of view, it's very complicated. So, and that's the problem with security. Usually we think of a problem as a static problem. We define the conditions and the constraint and say, okay, that's the best solution. Yes. But now when you try to deploy it, you have to look at the system as a living entity that has lots of changing parts. And if your solution imposes too much constraint on the system, then people will simply not use it, or if they are really forced to use it, they will find a way to circumvent it, and then the end user is your worst enemy, which is not something you want.
Okay, thank you. But I have another question, Mark. By analogy to the hardware, if we look at, because most of people right now dealing with AI, and what do you think? Against protection against adversarial attacks. At data processing level, but also at classification level. So and pertaining to what you mentioned for the hardware. We know all of us that AI applications are quite complex, and adding such kind of layer to detect vulnerabilities. What do you think about it in terms of performance or functionalities?
So AI, is a booming domain, as we know, and it's capable of doing absolutely fantastic things in natural language processing, image recognitions, and many other systems, or for classification, optimization, and stuff like that. Great. When it comes to security and when it comes to detection of vulnerabilities, I see lots and lots of papers being submitted to conferences, and very few of them pass the bar, because the problem is, people say, oh, malware, it's a classification problem. I have the goodware and I have the badware, and I just run my machine. I have, my test case, and I have my great CNN or whatever architecture they choose. And then they run the machinery, and then they generate the ROC curve, and they have the recall and the precision, and they declare victory. But no, that's not as simple as that. You have to convince me that it is what you are recognizing is really what you are recognizing. So I remember there was a paper where the authors had done a very important work to recognize bad websites. And they had a huge amount of websites that they had crawled and so on, and a very impressive work. And at the end, they were declaring victory because they were able just to submit the pages to an AI system, and it would say that's a malicious page or not. And they went the extra mile to try to understand why those pages were classified as this or that. And so they did some analysis, a bit like, if you want, similar to principal component analysis. It was not like that, but something like that. Long story short, they came out and says, oh, great, we found that actually one of the main thing was that these bad sites contain JavaScript. And so basically, it was not as simple as that, but it was the main reason why they suddenly were tagging the bad sides as being bad, because in their data set, they had no good side with JavaScript on it. And you say, that's absurd. This is ridiculous. I mean, you're not recognizing the right thing. And so if you want to do that, you need to have a representative data set. But what is a representative data set? Because the malware are evolving all the time. So yes, you may be good at detecting what you have checked and what you have been trained on, but it doesn't tell if you will be good for the next generation. Also, you have all the squealing attacks where the bad guys can now reverse engineer your system and find out, oh, these are the reasons why you generate an alert. Okay, I'm going to generate perfectly good pages, perfectly good ads, for instance, and I will put into that those elements, even though there is no attack. So your system now is going to generate tons of false positive. And if you generate tons of false positive, then the people, what will they do? They will shut it off, right? So there was this startup like 2-3 years ago in the antivirus world. They had raised huge amount of money because it was an pure AI antivirus solution. So they had declared that they had been able to train a system to recognize malware, and there was no signature, there was nothing, just that. And you just buy it and it would work forever. And some Israeli security company then bought the product and played a bit with it. And they realized that it was actually fairly simple to add to a real malware a bunch of code that was perfectly good but never activated, and suddenly the malware was not visible anymore. And they just published that, and the whole product was basically, crashed. I mean, it was just like, okay, sorry. So AI has potential, but as of now, for detection, I still have to see something which is very convincing to tell me that there will be no false positive, there will be no false negative. And last but not least, you need to be able to explain to me when you raise an alert, why you have an alert. You cannot just tell me, oh, the black box said it was a malware and I'm blocking it, because I need to be able to do something with that information. If you say, no, you're not allowed to, I'm blocking connection to that website, I need to understand why. And explainability in terms of layman, not explainability as it is done by AI people today, where they will explain to you in terms of equations and weights and stuff like that, which is perfectly good and already very complicated, but is not something that translates into something meaningful for the security analyst. And there, the semantic gap needs to be bridged somehow.
Okay, thank you so much, Professor Marc. I think we we don't have any further questions. So I'd like to thank you again for your availability for this clear presentation.